Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020. And this is the continuation of the lecture about the mean value theorem. When last I left you, you were in the midst of showing that this polynomial had exactly one real root. I hope many of you finished this problem, but if not, you know what to do. Let's see how you did. So we're to show it has exactly one real root. So we want to show that it has at least one real root at first. And to do that, we note that f at 0 equal minus 2. You just plug 0 in. And f of 1 is equal to 10. So you see this continuous function changes from being negative to positive between 0 and 1. And so that means it crosses every value between there. So since it is a polynomial, it's continuous. So by the intermediate value theorem, there is a number c between 0 and 1, such that f of c is equal to 0. So f of x has at least one real root. Now we need to show that there is only one real root, and we're going to use an argument that is called a proof by contradiction. We're going to assume that f has at least two real roots. And so that means we can find real numbers a and b, such that f of a is equal to f of b is equal to 0. But then we know that Rolle's theorem applies. So that means there must be a number c such that f prime of c is equal to 0. But if we take the derivative of this f of x, we will get 20x to the fourth plus 3x squared plus 7. You're squaring and raising to the fourth power numbers, and you're adding 7, this is never going to be 0. That's a contradiction, and that means that there are not at least two roots. So we showed that there was at least one, and there's not two, so there has to be exactly one. And that sets us up to come to the mean value theorem. If f is continuous on a closed interval AB and differentiable on an open interval AB, notice that's the same hypothesis as the Rolle's theorem, then there exists a number c in AB such that f prime of c is equal to f of b minus f of a, all divided by b minus a. Now if you think about this, this is kind of a version of Rolle's theorem slanted, because on Rolle's theorem we said this number was equal to this number, but if we rotate it a little bit, this is what we have. And so you see what we're really saying here is that the slope of this secant line, which is this expression, there's a point in between where the slope of the tangent line is parallel to the slope of the secant line. This is going to prove to be a very important theorem when we prove the fundamental theorem of calculus. Okay, so here's how the proof goes. So the equation of the secant line that passes through those points is this. There's the slope, we talked about that, x minus a, and this is y, and that would be y minus the y coordinate. Now we let g of x be the difference between f of x and y. Then g of x is the difference between that, and so it's the difference between these. Notice the sign changed over here. And so if we evaluate g at a and b, you see that g of a is equal to 0, and g of b is also equal to 0. So, and you have all this continuity and differentiability. So that means that we can apply Rolle's theorem to g. So that means there is a c in AB such that g prime of c is equal to 0. And when we take the derivative of g prime, we get f prime of c minus, and this is the slope, so that's what we get. Since this is equal to 0, that means that f prime of c is equal to f of b minus f of a all over b minus a. You see, Rolle's theorem was important in proving the even more important mean value theorem. Okay, let's do some examples of this then. So given f of x equal 5 minus 4 over x, we want to find, in this case, all values of c in the open interval such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Well, we have to calculate this, so we plug in 4, we plug in 1, we do the calculation, we find out that this ratio is equal to 1. So now we need to find out f prime of c. So we take the derivative and we get f prime of x is equal to 4 over x squared, and that has to be equal to 1. So we have to solve this. When we solve this equation, we find x is plus or minus 2, but we're looking for the answer that is in this interval, so we're only going to take c equal to 2. Here's a word problem. The two stationary patrol cars are equipped with radar that are 5 miles apart on a highway. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. He is legal at this point. 4 minutes later, when the truck passes the second patrol car, his speed is 50 miles per hour. Still legal. Prove that the truck must have exceeded the speed limit at some time during the 4 minutes. Well, you see, we're going to let t be the time in hours when it passes the first car, and then when it passes the second car, it's going to be 4 minutes over 60 minutes per hour is 1 over 15 hours. So we're going to let s of t represent the distance in miles traveled by the truck, and this is s of 1 over 15. And so what happens is that it was 5 miles was the distance between the two patrol cars. So what we're doing is the average velocity is the speed at the time it passes the second minus the first all over the distance between the two. But that says that the average velocity was 75 miles per hour. Now, since the position function is differentiable, that means that since the average is 75, there must have been a point somewhere in between where the truck was traveling at that rate of 70 miles per hour. So he would deserve to get a ticket, I suppose. A useful alternative form of the mean value theorem is if f is continuous on the closed interval differential on the open, then there exists a c such that, and we have this expression, which is just solving for f of b in the mean value theorem. Okay, so now we come to a problem, determine all values c, which satisfy the conclusions of the mean value theorem for the following function: x cubed plus 2x squared minus x on minus 1 to 2. This is more the kind of problem that I would ask on a test because I'm making you realize and remember what was the mean value theorem. You know what to do, and we'll see how you do when we continue in 25.2.